Okay, so we are now going to try to find the specific heat at these intermediate temperatures when they're not high extreme or low extreme. And we're going to do so using a method called the Debye interpolation. Now, we're starting where we ended with the low temperature approximation. And with the low temperature approximation, we had a double sum, and we approximated one of the sums as an integral for the k-states, because those k-states are close together, so this approximates some sort of density. And the idea here is we want to solve this as most explicitly as we can, but we still have to make some assumptions. Notice that I've got a 1 over v term here for the volume of what I'm working with, but this is a constant value. So what we can do is for the intermediate term, we can just drop this and throw it back in at the end as a scaling factor, because essentially this is going to be carried throughout, and to avoid forgetting when we have things and don't have things, we can just omit this for subsequent lines, and it's as if we have a volume of 1. But we can, for simplicity's sake, not write the term, so long as we remember to put this back in at the end. So what we're going to do is we're going to take the derivative with respect to temperature for these branches, these S photon branches, and we have 3 particular branches. And what we want to do is we want to simplify this, but this is omega S of k. And it would be very convenient if this omega doesn't really depend on k too much, or specifically even S. So what we can do actually is Debye had this clever idea where let's approximate these omegas as some constant value times the current k state they're in. So we're going to replace omega S of k with omega is equal to ck, where these are all constant photon frequencies at a particular k state. So at a k state, we have a particular frequency, which is equal to c times k. So we have our sum, our integral over the first Brillouin zone, and we have h bar omega S of k, which is really now going to be ck. And we have e to the beta, h bar omega S of k, which is now ck minus 1. And we'll have d, our k space vectors, 2 pi all cubed. Now, what we're going to do is we're going to change the spherical coordinates. So instead of having a kx, a ky, a kz, we're going to replace this integral over the first Brillouin zone with a triple integral. So d by dt, where we're going to go from 0 to some final k radius, which we're going to say kd. And we're going to go from 0 to pi, and from 0 to 2 pi for h bar ck over e to beta h bar ck minus 1. I'm going to have still my 2 pi cubed, but now I have to multiply by the Jacobian, which is going to be k squared, the sine of theta, dk, d theta, d phi. So right off the bat, I can see that I have something I can combine, and I've got some terms that I can pull to the front. So I'm going to say that the specific heat is equal to h bar c over 2 pi cubed our partial derivative, the s sums, and I'm going to have the integral from 0 to kd, our integral from 0 to pi, our integral from 0 to 2 pi, and that's going to have k cubed over e to the beta h bar ck minus 1, the sine of theta, dk, d theta, d phi. Now what I'm going to try to do is simplify this out. And I'm going to do so by looking at this term here and seeing that the only term that depends on on theta is sine theta. I'm going to look and see that nothing here depends on phi at all. So I can right away evaluate the integral at phi. So I'm going to have h bar c over 2 pi cubed. I'm going to have my integral of phi, which is 2 pi. And I'm going to have to put back in my partial, my sum, and my integrals now. 0 to kd, the integral from 0 to pi of k cubed sine theta dk d theta all over e to the beta h bar c k minus 1. Now I can see that I've got a 2 pi here and 2 pi cubed, so I can reduce that. So I've got CV is equal to h bar c over 2 pi squared. I've got d by dt, my sum of s. Now if I looked at my integral up here, I can see I've got a sine theta. So what I'm going to do is I'm going to integrate that out. So what I'm going to have here is negative cos of theta from 0 to pi, and my integral from 0 to kd of k cubed dk of e to the beta h bar c k minus 1. So what I'm going to have left here, the cosine of pi is minus 1. The cosine of 0 is 1. So minus 1 minus 1 is minus 2. Negative minus 2 is positive 2. So I'm going to have a value of 2 h bar c bracket 2 pi squared d by dt sum of s, the integral from 0 to kd k cubed dk e to the beta h bar ck minus 1. Now at this point I should notice that there is nothing to do with s. There's 3 branches. I can take this sum. So if I take this sum, I'm going to get 3. Because I'm summing the 3 branches, it goes from 1 to 3. There's nothing here that depends on s. There's no subscript, so I can just take that. So what I'll get here is CV. My sum is 3. If I notice here, I've got a 2, and I've got a 2 pi squared. If I was to expand this, on the bottom I'd have a 4 and a pi squared. Well, 2 divided by 4, I'm going to get a half. So I should have a h bar c over 2 pi squared. And I'll still have a d by dt, the integral of 0 to kd, k cubed for e to the beta h bar ck minus 1 of dk. Okay, so we're now going to try to push this derivative inside the integral and take the integral. Now we should notice that k cubed here doesn't have anything to do with t. The only term that has anything to do with t is that beta right in there. Now if we remember that beta is equal to 1 over kbt. So what we're going to do here is we're going to say, okay, well, CV is equal to 3 over 2 h bar c of pi squared down here. We're going to have this integral from 0 to kd, and we're going to take this derivative of k cubed over e to the beta h bar ck minus 1. And we still got our dk out here. Okay, so let's take the derivative of this thing, knowing that beta is the only thing that's got temperature involved. Well, to make this easier, I'm just going to write this as its own little separate line. And I'm going to have a term here of k cubed, but k cubed is a constant with respect to t, so I'm not going to worry about that. And I'm going to have my e to the beta h bar ck minus 1, and that's to the power minus 1. Now this That's the only thing with the temperature dependence, so I'm going to just try to solve that. So to me, that at the back, I can pull my k cubed to the front, and I'm just going to have the derivative of this thing. So I'm going to have a -1 times my bracket, and I have to subtract 1 from that. And now I've got to apply the chain rule here, so whatever was on the inside. So I've still got to do my d by dt of whatever's inside the bracket. Now, what's inside the bracket here, the 1 does not matter. It's nothing to do with temperature. But this exponential term has that beta. So what I'm going to do is I'm going to take the derivative of this term in order to respect to temperature. Now remember that beta is just 1 over kBt. So we got k cubed, the -1. I can just throw this term on the bottom for now. E to the beta hck minus 1 squared, and the derivative of this guy. Now if I plug in 1 over kBt, then what's going to come down here is my h bar, a c, a k. I'm going to have 1 over kb, and I'm still going to have this t, or this temperature part, which is on the bottom, I got to deal with. So applying the chain rule, I'm going to have a t here. It's going to get squared. It's going to get the negative associated with it because it was on the bottom. And that's the chain rule applied to that thing. So that's taken care of now. So I'm also going to have my exponential term. That's still there though. But this is the chain of this piece. So simplifying all this up, my derivative is going to be equal to k to the 4 h bar c. I'm going to have on the bottom e to the beta h bar ck minus 1 all squared. I'm going to have my exponential term here, e to the beta h bar ck, and I still have an extra term that is 1 over kb and 1 over t squared. Now if I multiply top and bottom by kb, then I can turn that into a beta squared. So I get beta squared kb. Now this is a lot cleaner than what we started with, so my goal now is to take this term, and we're going to continue over. So I now have CV is equal to 3 over 2 h bar c, this is over pi squared, the integral from 0 to kd, and I now have k to the 4 h bar c beta squared kb e to the beta h bar ck all over e to the beta h bar ck minus 1 squared dk. And we can try to simplify this up again. So I've got an h bar here, c, an h bar here, c, kb. I can pull a lot of this over as well. So I'm going to say, okay, cv then is equal to 3 h bar c squared, a beta, square it all, over 2 pi squared, times kb, is all in this integral from 0 to kd of k to the 4 e to the beta h bar ck all over e to the beta h bar ck minus 1 squared of dk. Now we got to make some substitutions.